Basically, blood enters the kidney and it goes through a series of tubes, which are arranged into loops. If you want to look more into this, there's the beautiful loop of Henle and other aspects of the kidney design that allow certain substances to be retained and other substances to be released, depending on how concentrated those substances are in the blood. The kidney responds to a number of hormonal signals, including vasopressin, in order to, for instance, antidiuretic hormone, in order to hold on to more fluid, if that's what your brain and body need. And it responds to other hormonal signals as well. So it's a pretty complex organ. Nonetheless, there's a key point, which I already mentioned, that I think most people don't realize. This is actually something that I like to tell kids when I meet them, provided that they're of appropriate age. I'll say, oftentimes if kids learn I'm a scientist, they'll ask a question about something related to science, and hopefully for my sake, it's something about neuroscience. But one thing that I'll tell kids, I'll say, do you know that your urine, your pee, is actually filtered blood? And occasionally that will really terrify a kid, but that also occasionally really terrifies an adult. But indeed, your urine is filtered blood. Basically, blood gets into the kidney. The kidney is going to filter out certain things. Certain things are going to be allowed to pass through, and others are not. Okay? So the way the kidney is designed is that about 90% of the stuff that's absorbed from the blood is going to be absorbed early in this series of tubes. And only a small percentage is going to be regulated or worked out as you get into what's called the distal kidney. I mean, distal just means the furthest part away. Okay? The proximal is up close. So like your shoulder is proximal to your midline of your body, and your hand is distal. So in biological terms, you hear about proximal distal, which just means near or far from. So just to give a really simple example, let's say that you are very low on fluid. You haven't had much to drink in a while. Maybe you're walking around on a hot day. Chances are that the neurons in your OVLT will sense the increase in osmolarity, right? The concentration of salt is going to be increased relative to the fluid volume that's circulating. This, of course, assumes that you haven't excreted a lot of sodium for one reason or another. But that increase in osmolarity is detected by the OVLT. The OVLT is going to signal a bunch of different cascades through the supraoptic nucleus, et cetera. And then vasopressin is going to be released into the bloodstream. And vasopressin, again, also called antidiuretic hormone, is going to act on the kidney and change the kidney's function in a couple of different ways, some mechanical, some chemical, okay, in order to make sure that your kidney does not release much water, doesn't make you want to urinate. And in fact, even if you would try to urinate, your body's going to tend to hold on to its fluid stores. Okay, so very simple, straightforward example. We can also give the other example whereby if you are ingesting a lot of water and it's not a particularly hot day and you're not sweating very much, let's assume your salt intake is constant or is low for whatever reason, well then the osmolarity, the salt concentration in your blood is going to be lower. Your OVLT will detect that because of these osmosensing neurons in your OVLT. Your OVLT will fail to signal to the supraoptic nucleus, and there will not be the release of vasopressin antidiuretic hormone, and you can excrete all the water that your body wants to excrete, meaning you'll be able to urinate. There's no holding on to water at the level of the kidney. Okay, very simple examples, but hopefully it illustrates how events within the blood, meaning the concentration of salt relative to the amount of fluid, right? That's what osmolarity is detected by the OVLT.